Hey guys, this is Professor Janacek, and I'm going to go over an application of Green's theorem. So, according to Green's theorem, the area of a region R enclosed by a curve C is the line integral over C of x dy, which is equal to the opposite of the line integral over C of y dx, which is also equal to half of the line integral over C of x dy minus y dx. So let's put all that together and take a look at this example. We want to find the area of the region bounded by an ellipse with major axis of length 12 and minor axis of length 8. Now, I want to remind you the equation of an ellipse looks something like x minus h quantity squared over a squared plus y minus k quantity squared over b squared equal to 1, where the center is hk, the major axis has a length of 2a, and the minor axis has a length of 2b. So looking at that, knowing that our major axis is length 12 and our minor axis here has a length of 8, we can deduce for this particular situation that a is equal to 6 and b would be equal to 4. Now we also have to remember how to write, so of course we could write the equation of this ellipse as x, the center is 0, 0, x squared over 6 squared plus y squared over 4 squared is equal to 1. But in this situation, it would be much easier to write it in parametric terms, in terms of, so looking at x and y independently. So the parametric equations, I should say, for this would be x is equal to 6 cosine t and y is equal to 4 sine t. If that's the case, then we know that dx is equal to negative 6 sine t and dy is equal to 4, hold on guys, back up. That is negative 6 sine t dt. Yes, we need that differential in there. And dy is equal to 4 cosine t dt. There we go. All right. That tells us we can now take the area. The area is, I'm going to go ahead and use the form that is 1/2 times the line integral over our closed curve C of x dy minus y dx. Notice I can use this one. I am, of course, looking at a closed curve. My ellipse is definitely closed, and I think this one's a little easier since we've got everything for it. Let's see. So that would be 1/2 times the integral from, I'm going to go ahead and use a regular integral. We're going from 0 to 2 pi of x, which is 6 cosine t, times dy, which is 4 cosine t dt. I'm going to go ahead and put that at the end. These are both going to have dt on them. Minus y, which is 4 sine t, times dx, which is negative 6 sine t dt. Again, I've kind of factored out that dt and put it there in the back. Looks like we can simplify this just a bit. This integrand, we have 24 cosine squared t plus 24 sine squared t. And I am liking that integrand because I think I can, let's go ahead and factor out that 24. So we have 1/2 times 24 times the integral from 0 to 2 pi of cosine squared t plus sine squared t dt. Sine squared t dt. And this is wonderful. Look at that, how beautiful. Love the trig simplification we can do here. Let's see, that's actually going to give me 12 as my coefficient times the integral from 0 to 2 pi of 1, which I don't need to write, dt. Oh, how awesome is that? Integrating dt, we just get t, so that's 12t, evaluated from 0 to 2 pi. Evaluating at 2 pi, we get 24 pi. Evaluating at 0 is just 0, so this simplifies to 24 pi. So the area of the region bounded by our ellipse is 24 pi. There you go. Enjoy!